Hey kids, so let's make sure this is still recording. Still recording. All right, taken two. All right, so we did pretty well with this. The electron configuration, how electrons are arranged to give you an address. That the sub-level, so this is the first energy level, and this is the second energy level, and 1, 2, this is the third energy level, is given by this number here, the green number. The sub-level, so the area of that energy level that is occupied with the electrons is given with a letter. It's S, P, D, or F. And then the number of electrons in that sublevel is indicated by this purple number as a superscript. That seemed to go pretty well. But now what we're going to do is, if this is the electron configuration on this side here, where it's a picture of Cardinal Gibbons, what we're going to do is magnify and look at even closer, where now we're starting to see more details as to which cars are parked and whatnot. So that's called an orbital filling diagram. And we are going to explore that right here. If you look here, here are some examples of orbital filling diagrams. Lithium, which is 1s2, 2s2, 2s1 rather, looks like this. You have an orbital for the 1s and you have an orbital for the 2s. Then there's orbitals available to the 2p, but they're just not filled with electrons because we only have 3 electrons. Beryllium, which is 1s2, 2s2, right here. So you're going to put 2 electrons in the 1s and 2 electrons in the 2s. So hopefully what you're seeing here, at each orbital, box or line can hold 2 electrons, right? Everything up here is holding, every line or box orbital here can hold 2 electrons in it, maximum. So that means the S would have 1 orbital so that it can hold its maximum of 2 electrons. The P will have 3 orbitals so that it can hold its maximum of 6 electrons. The D will have 5 orbitals so it can hold its maximum of 10 electrons. And the F will have 7 orbitals so it can hold its maximum of 14 electrons. That, since you know so much now with the periodic table, if we get back here real quick, right? Not even that one. Let's go to this one. Let's go to the, oh boy, Mr. Roach, why do this to yourself? All right, where's the one I want to do? There, this one. Okay, so you can count 14 down here, right? So this holds 14 electrons, so therefore there would be 7 orbitals. You can count 10 elements here, and so that would have 10 electrons, which is 5 orbitals. This can hold 6 electrons in the P, so that would be 3 orbitals, and the S can hold 2 electrons, 2 elements in there. So that would have, all right, so that would have space for 1 orbital. All right, so Hund's rule. Hund's rule says, if you notice again, looking at this picture, that when you have the 2p, so like this is 2p2 right here, 1s2, 2s2, 2p2. So the s's get together, the s's get together, but the p's, they don't go together. They could have gone here, right, and all jumped in one orbital, but they don't do that. Instead, they go to their own space. So that's called Hund's rule. And Hund's rule states that electrons, if a sublevel has more than 1 orbital available, electrons will occupy the empty ones first. So Quigley likes to call this the kids on the bus. If you get on this bus at this point, nobody is going to want you to sit right here, right? Because that's a little awkward. They're like, look, there's plenty of space on this bus. Why don't you go to one of the other spaces? And it's only when all the spaces are full that you start taking up these other seats. And the same is true with the electrons. If you look here, right, these are all p electrons. They're 2p3, but they all went to their own space. Only at 2p4 did they start doubling up. And then 2p5, they're doubled up twice. And 2p6, they're doubled up 3 times because there's no more room for them to go on that bus. So another way to think about this is cars, right? Seats in the car. So the s orbital is like a 2-seat car. And if you have 2 electrons in an orbital, one has to be going in the opposite direction of the other one. So one's going to be up and one's going to be upside down. And if you're in the P subshell, which is like a 3-row car, right? We got 1, 2, 3 rows here. So the first electrons will go in each row, and then the second electrons, when they occupy the same row, will go upside down, opposite to what the first one is. And then here, the D subshell, has 1, 2, 3, 4, 5 rows, and they will all occupy a row by themselves before they start going upside down. All right, hopefully that makes sense. Another thing to note here is as you get further away from the nucleus, right? So here's the nucleus, and here's the first subshell, or first energy level, second, third. All right, the sub-level energy levels get pretty close as you get further away from the nucleus, and because of that, we'll see a phenomenon here. So here's potassium, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So this is just showing you the orbitals for that 4s1, 4s2 for calcium. Scantium is 4s2, 3d1. Titanium 4s2, 3d2, 4s2, 3d3. And then we talked about here that some things jump and they do whatever is most energetically favorable. So you see here chromium, even though it should be officially 4s2, 3d4, there's a benefit to chromium pulling an electron out of this S and moving it over here so that it's all got 6 things going in the same direction. Now I'm going to try to demonstrate this in class with hula hoops, why that's an energetically favorable thing. God help me if I do that. But anyway, you don't need to predict this, but hopefully you will understand that it's an energetically favorable thing, and that's why it occurs. That's my point with that. So anyway, let's look at some examples. So carbon has an atomic number of 6 on the periodic table. We're going to assume 6 electrons. So doing our electron configuration, the first 2 will go in the 1s, the second 2 will go in the 2s, so that's a total of 4. That's 2 plus 2 is 4, and so we have 2 more electrons left, and so that'll be in the 2p, and that'll be 2p2. So orbital filling wise, we would assign a box. I mean, let's make it a box. It doesn't have to be a line, but if it helps you see this better. So a box, that would be the orbital of 1s, and it has 2 electrons in it. The orbital of 2s would have 2 electrons in it, and the orbitals of 2p would have a total of 2 electrons in it, and we're going to put those electrons into separate 2p orbitals. So we can try again with phosphorus. Phosphorus has an atomic number of 15. That'll be 1s2, 2s2, 2p6, 3s2, 3p3. And orbital filling wise then, the 1s has an up and a down because there's 2 electrons in it. The 2s, same thing, an up and a down. The 2p is going to have 3 orbitals, and each one goes up and down. Then the 3s has a full one, and then the 3p, in this case, has 1 electron in each one going up. All right, so 3 electrons going on their own space on the bus, kids on the bus. Now, another thing you might notice, you can write shorthand on these, and you don't have to do this if this is too confusing to you. You can always just write everything out. But you see how the noble gas argon is 1s2, 2s2, 2p6, 3s2, 3p6. Now, titanium, which comes after argon, is number 22, which is after 18. It has everything that argon has in it, right? That's the exact same thing as argon, so we can call this argon. Plus a 4s2, 3d2. So if you ever want to write shorthand and not have to write all these, you are more than welcome to say that the orbital, not orbital, the electron configuration for titanium is everything argon is plus the 4s2, 3d2. So you see how this, change the color here, right? So this here is this here, and then the argon is the red, right? So this argon here is all this stuff here. So you're allowed to do this with what's called noble gases only, right? So the noble gases are the last part of the, let me escape this here all day, but yeah, the noble gases, hopefully you know now, are these group here. So you can only do that for the group in here at the end of the periodic table. All right, so I think that's pretty much everything. A nice thing for you to do if you want. So here are the noble gases here in yellow. Another thing that I will let you know about is I will put this on my webpage as a resource. But if you want to test yourself for any of these, you can go to Orbitals and then just choose any element. And here, up in here, it'll show you what the orbital filling diagram is. And up in here, it'll show you, whoops, up here, it'll show you what the electron configuration is for that atom or neon or whatever. All right, so hopefully that's helpful to you. But you can test yourself on any one of these. It'll show you the orbital diagram, and it'll show you the electron configuration up here. All right, hope that's helpful. Let me know if it's not, and I'll talk to you later.